Welcome back. So we're continuing to set up and solve systems of equations to find values for x and y that we can plug into our optimization equation and actually maximize it. We cleared off all our constraints right here. We have them written down right here for reference. We just wanted a little bit of room to write here. So we need to set up two more systems of equations, one for these two intersection points. We've plugged in these for these two intersecting points. Now we find out what these two. So we have the blue equation and the yellow equation. So we have, or whatever color equation is, I haven't figured it out yet. So we have the equation 80,000 minus x equals, well, y is always going to equal 0 here. So this will actually be fairly simple. These 2 points will be. So we can add x to both sides. Those two will cancel. So we have x is equal to 80,000. And y is always going to be equal to 0. So we're going to have 80,000 and 0 for this solution point. So 80,000 and 0. All right, now we have one more to check. We have this intersection point to check, which is the purple line and whatever color this line is. So we have the equation 100,000 minus x is equal to 0. And this one's pretty simple too. So we add x to both sides. And we get x is equal to 100,000. And y is always going to be equal to 0 in this case. All right, so we have the solution point of 100,000 and 0. Okay, so we have x and y values for all four of the corners of our feasibility region, which we know that one of these four intersecting points will be the maximizing values for our optimization equation. One will also be our minimizing values, but we're not worried about that. We want to maximize our profits. All right, so now we're going to go ahead and plug in the x and y values one at a time into our optimization equation and see which one will give us the greatest value. So let's start with this one. We have 80,000 and 20,000 for x and y. So we have z equals 12,000. 12,000 minus 0.09 times x. X is 80,000 minus 0.02 times y, which is 20,000. And we can go ahead and solve this. So we have 12,000 minus, we have 0.09 times 80,000, that will give us 7,200, excuse me. 0.02 times 20,000 gives us 400. And this will add up to 4,400. So we have 4,400 for these sets of values. So let's go ahead and write this. For this, we're going to have $4,400 is going to be the return on our investment for these particular values of x and y. All right, let's go ahead and try another one. Let's try this point, 64,000 and 36,000. So we have z equals 12,000 minus 0.09 times x, which is 64,000. 64,000 minus 0.02 times y, which is 36,000. And let's go ahead and solve this. So we have 12,000 minus 0.09 times 64,000 will give us 5,760. Then minus 0.02 times 36,000 will give us 720. And this results in $5,520. So this is going to result in a return of 5,520. All right, let's go ahead and clear a little space here so we can check our other 2 points. Our next point is 80,000 and 0. So let's plug that into our optimization equation. We have z equals 12,000 minus 0.09 times x, which is 80,000. 80,000. Then we have minus 0.02 times y, which is 0. So anything times 0 is 0. We don't even need to write that second or that last bit of information. So we have 12,000 minus 0.09 times 8,000 is 7,200. which gives us $4,800. So we'll have a return of $4,800 with this investment strategy. And we have one more to do. We have 100,000 and 0, so let's go ahead and plug that in. We have 12,000 minus 0.09 times 100,000. I have a feeling this is going to be less than the first or this previous one. We have a value of y equals 0, so that term's going to cancel just like above. So we have 12,000 minus 0.09 times 100,000. 9% of 100,000 is just 9,000, which gives us 3,000. That's actually the lowest return of all 4 investment strategies. Okay, so we've plugged in all 4 points into our optimization equation, and we can conclude that our maximum profit, our max profit, or our ROI, our return on investment, is going to equal this right here, $5,520, $5,520, and it occurs at the point 64,000 and 36,000. 64,000, that's a 4 right here. Okay, which means that $64,000, since X equals $64,000, and we defined X as the amount invested in bonds, so $64,000 invested in bonds, and Y, well, we defined Y as the amount of money invested in gold. Well, $36,000 invested in gold. That's a V right there, by the way. So $36,000 invested in gold. So $64,000 in bonds, $36,000 in gold gives us $100,000. Remember, we only had $100,000 to invest in the beginning, which means our third investment of stocks will be 0. We're not investing anything in stocks, the stock market or the index fund. We called it a few different things. So this is actually going to maximize, give us the maximal investment return of $5,520 when we use this strategy: $64,000 in bonds, $36,000 in gold, and 0 in stocks. Now, this isn't the complete maximization of the investment strategy. These are only the best given scenario for the constraints that we set. Remember, we set some constraints where, such as, if I remember correctly, bonds needed to be 4 times the amount invested in bonds as in gold. We wanted to play it safe and put no more than $20,000 in the stock market and such. So given the constraints, this will be the best investment strategy to maximize our return on interest. So I hope this was very exciting. This was actually very interesting, and it's shows you that linear programming can be very useful, especially in the world of finance and investments, and can help you make or save a lot of money. We'll actually do one more application in terms of linear programming when we're actually dealing with a company that's manufacturing some products. So I'll see you in the next video.